topic of variational methods, and just to sort of recalibrate where we were before the break and what we did last time was basically this big picture view of pretty much all of the stuff that we are covering in chapter 5, parts of chapter 9, and then the next chapter that will cover chapter 6. All of this stuff is sort of captured by this big picture view. We know what a strong form is. That's basically your governing differential equation, something that for three-dimensional problems looks like divergence of S plus B equal to 0, or for a one-dimensional problem, it looked something as simple as this. We are trying to solve this problem. Okay, one of the ways that we said was to convert the strong form of the problem to a weak form, and in order to do that, we had to use the method of weighted residuals. What was the method of weighted residuals? Take the governing differential equation, multiply it with u bar, integrate it over the domain, add some boundary terms, and then do integration by parts to come up with this g functional, where there was one derivative on the real displacement, one derivative on the virtual displacement. That was the PVW form of the weak form, if you remember. We came to the same PVW form of the weak form from a energy functional. So that's an energy functional approach that we did, I think, last time and maybe last to last time, where we write the energy stored in a structure and the change in potential due to conservative external forces. So we said that if we write that pi, which hopefully you all remember, when we said like this was the pi functional for the one-dimensional problem that we had laid out. If we minimize that, which we did last time, we minimize that using the directional derivative, definition of the directional derivative, and set minimize derivative equal to 0, which gave us back this that the minimization of the energy functional gave me the virtual work functional. So that's again fits nicely into this big picture. If you start with pi, minimize it, you get back to the same virtual work functional. And later on in chapter 6, we'll see that this virtual work functional is the one that we will approximate, where we will plug in some approximation for the real displacement, plug in some approximation for the virtual displacement, and then we will get an approximate numerical solution for these types of problems. Because the strong form itself is difficult, let me see if I can just disable this. Maybe not. Disable. All right. So so ultimately what we want to be able to do is to go between all these three different forms of the problem statement. We know that the strong form for general three-dimensional big problems is not solvable. That's why we constructed this weak form. I showed you that you can construct this weak form from an alternative approach, and then we'll try to find approximate solutions to this particular weak form. One question that we did not answer completely last time was, how do we go from this weak form to the energy form? And last time I was mentioning that for this to happen, the conditions of the Weinberg theorem must be satisfied, which essentially says that G functional, the virtual work functional, must be linear in the second argument, and its directional derivative must be symmetric in the second argument. And if that's true, then the energy functional corresponding to a virtual work functional would be given by G of TU, where T is just some parameter, U is the displacement, the real displacement function. Integrate with respect to T. T is not necessarily time; it's just some parameter. And from the definition of G, you will be able to get pi. And we were going through this example last time of this one-dimensional problem. For this one-dimensional problem, we have already constructed the strong form, we have already constructed the weak form, and we have already constructed the energy form. So for this particular problem, we already know that going from here to here is possible because we already know that this exists. But still, we are going through the logic of the Weinberg theorem to see and to make sure that indeed we can find this energy form starting from the principle of virtual work form as well. And that's what we were doing last time. So we checked that this G functional, this was the principle of virtual work form of the weak form. So I write PVW form of the weak form. And we had already checked that last time that this is indeed linear in the second argument. And we had checked that it is symmetric. The directional derivative of G is symmetric in the second argument. Because what we found last time was that dg of u comma u1 bar in the direction of u2 bar is the same as dg of u2 bar in the direction of u1 bar. And these two are exactly the same. So so it means that Weinberg theorem conditions are satisfied, which means pi u exists. Okay, and how do we find pi u? We just go back to the definition of the Weinberg to the theorem, Weinberg theorem, and we see that pi u can be obtained in this manner. So let's do that. We'll write pi of u would be equal to g of tu comma u integrated with respect to t between 0 and 1 and plus c. That's the definition. That's the expression for pi u that Weinberg's theorem gives. Let's plug in all of this. So I'll put integral 0 to 1 outside. In this big square brackets, I will write out a big G functional where all that I will need to do is to substitute in this G functional. I will substitute t times u wherever real displacement occurs, and wherever virtual displacement occurs, I will replace it with u. Okay, so G of u comma u bar was originally given to me. What I'm trying to find is G of tu comma u. Right, so we'll do that. What we get is integral 0 to L of u bar c t u bar dx and minus integral 0 to L of u comma ub dx and minus, I'll write it in blue, the boundary term, minus u of L TL, and I'll close the square bracket and dt and some plus constant c. So all I've done in the expression in this square bracket is just replaced. If you remember, we were given G of u comma u bar, correct? All I'm doing is I'm replacing u with tu and u bar with u. That's all I'm doing in the original definition, and hopefully you all see that this is what we get. At this point, I'm ready to integrate this. And since t is just a parameter, it does not depend upon x. I can pull all of those integrals or all of these integrals inside the integral for x. The only thing that depends upon t is right here. Okay, so if I rewrite this expression, what I get is integral 0 to L u bar or u prime times integral 0 to 1 of t dt. That thing is here, u prime is here, dx minus integral 0 to L of u b dx minus UL TL and plus C. So hopefully you can all see that all I did here was to take the integral for t inside, and the only place that it's useful is here. All of the other places you would just get integral dt between 0 to 1. That would just be 1 itself. Okay. Here you can see that that this entire term, what is the value of that entire term? Integral of t dt is t square over 2, correct? T square over 2 between 0 and 1 is half. So what we get is that this value is half, which means that pi u, according to the Weinberg theorem, is equal to half integral 0 to L of u prime c u prime dx minus integral 0 to L u b dx and minus ul TL and plus some constant. Let's check whether this is the same pi u that we got originally from our definition. So half of u prime times cu prime. If you roll back to where we derived this, half of c u prime square minus ub dx. I think this dx actually should be out here in your handouts. You can change that. This dx should be out here. The body force term should also be within the integral, and minus ultl minus u0t0. The only term missing from that expression is this minus u0t0, which actually is not something that you can obtain from the weak form, because we know that in the PVW form of the weak form, in this PVW form of the weak form, we had already assumed that the virtual displacement must be 0 where x is where the displacement where the real displacement is specified. So we cannot get that term. In fact, if you were to not use the assumption that that the virtual displacement is 0 where the real displacement is given to you, in that case you would get the other u bar 0 and t0 term as well. But this would be the correct energy functional for this one-dimensional problem that we had found. So indeed, and there is this constant. Any idea why there is this constant up here? This is energy, total energy. So there's no way you can define a 0 energy state. So somewhere you have to say that this is, for example, in a potential energy, I'll say maybe this book lying on the table is 0 energy state. If I raise it, its potential energy increases by this amount. So somewhere you have to have a datum for an energy. That's why this constant is there to calibrate between different datums. All right. So in essence, what we have done is, going back to this big picture view, we have found a way to jump back and forth between these three different forms, from a strong form, method of weighted residuals, integration by parts, to weak form. Now, if this weak form satisfies the Weinberg theorem conditions, then we can find pi u as well. Alternatively, if I have pi u, I can minimize it, find the same weak form, and do reverse integration by parts, apply the fundamental theorem of calculus of variations to get back to the original strong form. So being able to jump between these three different forms is what is something that you have to be able to do. It's only algebra, but big picture conceptually is captured by this in this manner. All right. So what I'll also do is try to correlate it. This is an aside. This is not there in your books, but since we talked about variational principles for static problems, I wanted to just mention that there are indeed variational principles for dynamic problems. For static problems, the governing equation for equilibrium was divergence of S plus V equal to 0. For dynamic problems, there are inertial effects also. For example, if you kind of correlate it to this simple picture that we saw for a mass and spring system. In statics, if we are trying to find the displacement, that would just be mg over k. However, if you are looking into dynamics of the system, then mass, spring, and if you apply a force, obviously it will oscillate before it comes to a steady state. Okay. Even for these types of problems, there are energy-based principles to come up to this. Now, Newton's law would say that if I stretch it by u at a particular instant of time, if the displacement is u, the spring force at that instant of time would be ku. External force acting is F. If these two forces are not balanced, then the acceleration of this mass will be given by F minus ku divided by m. And that gives me this well-known equation of motion that we write for a single degree of freedom system, right? The same equation can be obtained by using an energy principle, not requiring the use of any Newton's laws. So, how do I do that? In order to do that, I will try to set up, try to imagine what the trajectory, for example, what the trajectory of this single degree of freedom system would be. Let's see if that helps. So, for example, if I take this single degree of freedom spring system, stretch it, leave it, it would just oscillate like a sinusoid, correct? So if I were to plot the trajectory of that particle, it would be like a sinusoid kind of going like that. Okay. Now, if I pick two instants of time in that trajectory, then what I'm trying to find is this path. How does the displacement of the particle go between T1 and T2? This black path is what I'm trying to find. Okay. Now, a variational approach or an energy-based approach says that let's say I don't know that path, I will consider paths, other possible paths of that particle, which are sort of given here in the blue dashed lines, U bar. Those are the virtual displacement paths. So in that way, what I can do is to write the kinetic energy of the particle at a particular instant of time. That's half mv square. U dot is just velocity, half mv square. Potential energy of the particle, that would be equal to the energy stored in the spring, half of ku square, minus the change in potential due to the conservative force. If I have displacement u, force is also in this way, that will lead to a reduction in the potential. So now what is defined, an energy functional is defined, which is called this Lagrangian, where we the definition of the Lagrangian is kinetic energy minus potential energy. There's an alternative definition in this Lagrangian is a function of displacement and velocity. There's a different functional called the Hamiltonian, where you actually express it in terms of displacements and momentum. Momentum, if you remember, of course, is mass times velocity, which is much more sort of physically appealing, that energy stored in a particle would be kinetic energy plus potential energy rather than kinetic energy minus potential energy. But it so turns out that this definition of Lagrangian will lead to the right system of equations. Once we have this Lagrangian at a particular instant of time, we take the integral of that Lagrangian between T1 and T2, from here to here, considering all possible alternative paths u bars, and we take the minimization of that integral, which is called the action integral, in the direction of all possible virtual displacement paths to be equal to 0. This is very similar to minimizing our energy pi u. Okay, and after a bunch of algebra, which I will not go through in detail, I'll let you read it. You will see that what we get is U bar times mu double dot minus ku plus f, which tells me that if for this equation to be 0 for all possible u bar, the only way that can happen is if mu double dot plus ku minus f, which is this equation, must go to 0. So starting from the definition of kinetic energy, potential energy, writing an energy functional, taking the minimization of that, exactly what we did for the static problem, gives me now equation of motion for a dynamic problem. So this was just an aside to let you know that these variational principles of energy that we have been talking about, this is not just for static problems. Even for dynamic problems, there are actually multiple variational principles for dynamics that people have derived. And as I mentioned, this type of an equation that you obtain from an energy approach, that if you why this keeps jumping on me. If you start from an energy form, which we just did for the dynamic problem, minimize it, get to a virtual work form, do reverse integration by parts and all that to come to the strong form. This type of equation is called the Euler equation or the Euler-Lagrange equation corresponding to this energy form. Okay. All right. So if you're interested in that, you can. There are some of the books in the course syllabus that I mentioned, and actually there's a course at Purdue called Variational Principles in Mechanics, I think in aerospace, that you might want to check out. But in any case, the corresponding three-dimensional deformed equations you would obtain would be divergence of sigma plus b. That was the static part, and now for dynamics you add the inertial effects. All right, so that's all I'm going to say about this. And as a last thing in this chapter 5 of developing these weak forms, what we'll do is go back to this picture. Go back to this picture. And we have seen how to do this, go between strong form, weak form, and energy form for a one-dimensional problem, for that one-dimensional bar where the governing equation was simple, a scalar equation essentially. We're going to try to do that same thing for a big three-dimensional problem, which is basically something like this. I have a three-dimensional body. Essentially what I'm talking about now is to develop a weak form for this problem. Okay, this was the original strong form of the 3D or the 2D problem that we aim to solve. We are going to try to develop a strong form for a weak form for this problem now. So how do we begin? If I know the strong form of the equations and I want to find the weak form, what is the first thing I do? Say it again. Write the functional equation, which would be which functional equation? Right. So if I have the strong form, I need to go to the weak form using the method of weighted residuals and integration by parts. That's what we'll do. All right. So to write the method of weighted residuals form of the weak form, it's very simple. You just write the governing differential equation, divergence of S plus body force, that's the left-hand side of that equation. Multiply that with u bar, integrate it over the entire domain of the problem, dV. Okay, and I'll add the boundary term. The boundary term is plus integral of T sub n minus Sn, right? That's the natural boundary condition. D area over gamma n. So I'll explain all of that and put a square bracket around the whole stuff, and don't forget the negative sign, just for convention. That was my method of weighted residuals form of the weak form. Exactly what we did for the 1D problem. Now we have written the same thing for the 2D or the 3D problem. And note that the boundary term I'm writing only on, oh, sorry, I'm missing something. Even on the boundary term, I have this U bar. Okay. So this is very similar to what we did for the one-dimensional problem. You remember we had the governing equation multiplied by U bar integrated over the length of the bar, plus U bar 0, boundary condition at 0, and later on we set U bar equal to U bar at 0, where the boundary was fixed. We set that equal to 0, so we got rid of this entire term, correct? And U bar L times TL minus sigma L. This is nothing but traction is equal to stress times normal. At L. So the two terms that I have written in the corresponding 3D form is this term and this term, assuming that the virtual displacement, wherever the real displacement is specified, is set to 0. That's what we have done here. So these are the two terms that we get. If we write that same thing in initial notation, hopefully you can all see that U bar would be just U bar I. S, divergence of S would be Sij comma j. B would be Bi, U bar I, Tn, I component, Sij acting on Nj. So all I've done is written that in initial notation. And after that, I'm again going to do integration by parts. So in the to be able to do integration by parts, what I'm doing first of all is to try to express this term using the product rule of differentiation on these two terms, U bar sigma. This is exactly the same step that we did for the 1D problem, which, let me see if I can pull it up right here. For the 1D problem, we said product rule on U bar sigma, and then found that this particular term can be expressed as U bar prime sigma minus some boundary term. That's exactly what we are going to do for the 3D term as well. So U bar sigma by the product rule gives me this. This term is right there in your in this weak form. Substitute that, go through some algebra, and if you remember in the 1D case, what we did was we used integration by parts to shift one of the derivatives from the real displacement to the virtual displacement. Do you remember that? There was Cu double prime, and we shifted one of the derivatives on the real displacement to the virtual displacement. That was integration by parts. The corresponding operation in 3D is just divergence theorem. That derivative of this quantity is given by St acting on N. So an integral over the volume becomes an integral over the boundary of that domain. So I'll even write here, this is similar to integration by parts by for the 1D case. And again, I'll let you go through the algebra. I don't want to go through too deep into the derivation, but essentially what you should be able to see is that starting from the strong form, we write the method of weighted residuals, take the product rule, do integration by parts, and then cancel off some of these terms. Let's see which ones cancel off. We can, what we see is that this particular term, minus of U bar I Sij comma j becomes U bar Sij Nj from the divergence theorem, and we get this boundary term out here. So let's see which ones cancel off. This first term, note that this term is over the entire boundary. This first term goes to 0 because this is the virtual displacement on the portion of the boundary that has real displacement specified. So this is because of homogeneous essential boundary conditions. That's the condition that we have already assumed. And I think maybe in your handouts this particular term was written as T sub D, but essentially it's stress acting on the normal, that is traction. So maybe I'll mention that. In your handouts, this must have been written as T sub D I. Okay. But the virtual displacement on that portion of the boundary is 0. Now, the other term that we get from the boundary term is Sij Nj over gamma n, which is the traction boundary. This term is negative. Negative and negative here is positive. So that part of the boundary term goes away with this term. So I have cancelled off this entire term because gamma d and gamma n, both of those terms go to 0. So this entire term drops out. And what I'm left with is minus ui ti on the portion of the boundary that the tractions are specified. So ultimately, we are able to express all of that in this particular form, which is the PVW form of the weak form. So this now becomes the PVW form of the weak form, where the functional g, it's still a scalar function of a vector real displacement, a vector virtual displacement, virtual strain, real stress, real Cauchy stress, that was the internal virtual work, minus virtual displacements time body force integrated over the domain, and minus virtual displacements time external tractions on the traction boundary. What does this mean essentially? If I have a structure like this, boundary, if you remember, left boundary was fixed, there was some loading on this part of the boundary, then we calculate the energy, not the energy, but the internal virtual work stored in the deformed body, and that's this term. And the external virtual work done by the body forces and the tractions is given by this WE term. Exactly what we had for that one-dimensional problem. It's very analogous what we did here to the original one-dimensional problem. It's, of course, the math is a bit more involved, but essentially it's the same idea. And finally, since we have gone from the strong form to the weak form, we can extend that to the energy form just by using Weinberg's theorem. You can show that actually it is satisfied, and if we find the energy functional from this virtual work functional using that expression of the Weinberg's theorem, there is a plus c that I'm not writing here. You can show that all of this gives me the corresponding energy form of a three-dimensional solid. So if you have a three-dimensional structure or a solid body that has some deformed shape, you can calculate the strain energy stored in this deformed body by this first term. And during or as the body is deforming, there is change in potential due to external conservative forces, which are the second two terms. Exactly what we had for the 1D bar problem. Okay, so all of this machinery that we are developing to find approximate numerical solutions, essentially by using this sort of a weak form, that we did for the one-dimensional bar problem, is also perfectly valid and applicable to 2 dimensions and 3-dimensional problems as well. All right. So this part of the exercise was just to show you that what we are developing is applicable to 2D and 3D problems. We are obviously not going to be able to delve too deep into 2D and 3D problems, because as you saw maybe last week or last week in that Friday review session, even for a one-dimensional bar problem with a very simple approximation of 2 terms, it took us half an hour to get to the answer by hand, right? For complicated 2D and 3D problems, you simply cannot, well, you can, but it would be extremely cumbersome to try to do that by hand, okay? But at least the logic of all of this that we are developing, even for the, whatever we are learning for the 1D problem is perfectly valid and applicable to 2D and 3D problems. So this, how to work with this virtual work functional. And for those of you who might be taking finite elements next semester, you should likely see this virtual work form or the weak form. This is where you will make approximations for real displacement, approximation for virtual displacement, like some combination of polynomial functions or something. Plug that approximation in here and get some approximate solution, even for a complicated structure like the one I showed. And that's actually a simple structure considering the different types of complicated structures we encounter these days. All right, so that's pretty much what I want to say about strong forms, weak forms. Keep this picture in mind, okay? Strong forms, weak forms, and energy forms. We should, the details and the algebra is not as important as being able to understand conceptually what these three different forms are. Essentially, they are solving the same problem, okay? So I'll give you a little taste of how to actually do the numerical approximate solutions using these weak forms. And that's the focus of this chapter 6 that actually I even covered a little bit in the Friday review session. So ultimately, what we want to do is to solve this strong form, a bunch of partial differential equations, some boundary conditions, over a three-dimensional object, okay? We know that we cannot solve that exactly. So what we did was we came up with a corresponding weak form of the problem statement, where we said that what we are trying to do is to find the displacement field at each point. Displacement is a vector field, 3 components x, y, z, strain field, stress field, such that the real displacement is in H1 space of over the body, over the deformed body. And actually, since we'll restrict ourselves to small deformations, you can kind of make a sweeping approximation and freely interchange x and z. So what we are trying to find is displacement, strain, and stress fields that satisfy the strain displacement relationship here, that satisfy the stress strain or the material property relationships here, and that the real displacement has to be equal to the given displacement on the boundary that is fixed. Okay, so that's something that was the essential boundary condition in our weak form, if you remember, such that G functional that we just saw on in the previous page on chapter 5, it goes to 0 for all possible virtual displacements also in H1 and satisfying the homogeneous essential boundary condition over the boundary over the entire body. This was the weak form corresponding to this strong form statement of the problem. Both of these are equally hard. We cannot solve this weak form exactly either. Okay. So what we are going to do is to try to understand how can we get approximate solutions to the weak form, which would be approximate solutions to the original strong form as well. That I'm just writing the same strong form for the 1D problem and the corresponding weak form for the 1D problem that we had seen. And as I just mentioned, from that big picture view, strong form, weak form, energy form, what we're going to take is this PVW form of the weak form, this guy. And we are going to now plug in approximations for the real displacement, plug in approximations for the virtual displacement, and get an approximate weak form that we can actually solve. And that will lead to these types of equations that, if you remember, we saw Friday session. But okay, let's see how to do that. One way to generate these approximate solutions is with this Ritz method. Okay, what this Ritz method says is that if I'm trying to solve a problem like this for this particular boundary condition, what I need to do is to approximate the real displacement and approximate the virtual displacement in that weak form. So what I want to do is approximate the real displacement with u, h, x, and I will do that by writing this as a linear combination of some functions. So before I do that, can anybody tell me what are the conditions that the real displacement must satisfy? Let's just go back to that previous page. What conditions must the real displacement satisfy? These conditions right here, right? That it has to be in H1. So any function that I choose for the real displacement has to be in H1. What is H1? First derivative square integrable, right? What kinds of functions are these? Anything that is not discontinuous, right? A function can have a kink, but it cannot be discontinuous, because derivative of a discontinuous function at the point of discontinuity would be Dirac delta. Dirac delta is not square integrable, right? So a function can have a kink in it, that's perfectly fine, but it cannot be discontinuous. So all these functions all of those types of functions we can choose for approximating the real displacement. In addition, we must make sure that the real displacement, wherever the real displacement must satisfy the essential boundary condition, that whatever is displacement given to me at x equal to 0, for example, has to be satisfied. So this is the more tricky part of the real displacement approximation. So in order to do that, since I know that somehow I need to pick functions which go to a value of u0 at x equal to 0, what I'll do is I'll go pick something here, the value u0, and I'll say that I'll pick some function, could be any function, any odd function out here. Whatever it does in the remaining part of the domain is immaterial. The only thing that it must do is it must go to u0 at x equal to 0. Okay. If I do that, and let's me call this function h0 of x. Okay. Then what I will do is I'll choose all other functions, h1, h2, h3, and so on. I can choose all of those functions. Could be a function like this, could be a function like this, could be some other function with a couple of kinks in there, could be sinusoid, doesn't matter. And it can go to any value at x equal to L or any other place, but at x equal to 0, all of these functions that I'm drawing, h1, let's say h2, h3, all of these functions have to be continuous, and they have to be essentially they have to be in h1, and they have to go to 0 at that point. If I do that, then I can write my approximation as, let me write this as h0 of x plus some unknown constant a1 times h1 of x plus some unknown constant a2 times h2 of x, and so on. Do you agree? Do you agree that if I approximate my real displacement in this manner, then whatever the value of a1 and a2, which we will calculate later on, whatever that value of a1 and a2 be, that this real displacement would actually be in h1, and the value of that use at x equal to 0 would be u0, right? Because all of these h1, h2, h3, all of those functions go to 0 at this point. The only non-zero function at x equal to 0 is h0. So this h0 function helps me satisfy the essential boundary condition. All of these h1, h2 and the other functions that I might choose, they are 0 here. So this real displacement would be in h1, and it would satisfy the essential boundary condition. What I'll also do, just take a couple minutes here. I'll write this in a slightly different form. I'll write this as h0 of x plus a horizontal vector of a1, a2, a3, all of these coefficients, unknown coefficients for now, and times a vertical vector of h1 x, h2 x, and up to whatever hn x. Right? So a horizontal vector times a vertical vector gives me back that sum, a linear combination of all of these functions. Okay. So in essence, if we do that, then we get the approximation that that u of x is approximated with u h. H is supposed to denote that this is an approximation. X equal to h0 x plus a, let me write that red, a vector transpose times h vector x. So all I've done is all these unknown coefficients I'm representing with this a transpose vector, and all of these h functions I'm representing with this vector function. So this is an approximation for the real displacement. And very similar way, I have to also approximate the virtual displacement. So for that, one of the most common things that people use is called the Galerkin approximation, where we use the same space of functions as the real displacement. Let me ask you this: Can I write the exact same expression just by so maybe I'll do that. h0x plus a1 bar h1x plus a2 bar h2x and so on. Can I do that? Would this be a good choice for the virtual displacement function? What are the conditions that the virtual displacement must satisfy? It also has to be in h1, so that's fine. All of these functions are in h1. They are all first derivative square integrable. But in addition to that, the virtual displacement must also satisfy, where is that? Here. That basically says that u bar x has to be equal to 0 at x equal to 0, or gamma d, right? Which means that this particular term out here is not needed. Okay, so the virtual displacement is very simply just a bar vector transpose times all of the same functions of h. Maybe next time what I'll do is I'll tell you how to choose these functions and then substitute that into the weak form, derive a matrix form, and a matrix form that can be easily solved on a computer. And I'll actually give you a MATLAB code to do that. All right, so let me stop here. We'll see you back on Friday.